Hi, welcome to Chapter 12, Part 2, where we're going to talk about ionic solids, molecular solids, and covalent network solids. So ionic solids are held together by electrostatic attractions between the cations, which are the positive charge, and the anions, which are the negative charge. Ionic solids have very high melting and boiling points and are what you basically think of as a crystal. Most of the time you're thinking of an ionic solid. Because the charge is centered on the anion, they are electronic insulators. So when they are in the solid state, ionic compounds are in solid state, they do not conduct electricity. You either have to melt them and make them molten or dissolve them in order for them to conduct electricity. The most favorable structure have cations and anions distanced as close to each other as possible. Remember, in part 1 of chapter 12, we said that the atoms want to pack as close to each other as possible. While we're doing this, we also have to make sure we maximize the difference between the anion-anion and the cation-cation relationship. And as a result of this, for some structures, for these in particular where we have one-to-one, one cation, one anion, you form these cubic lattices. Either the primitive cubic lattice, remember, we talked about this in part 1, where the atoms are on the corners. Or you could have face-centered cubic, where the atoms are on the corners and they are on the face. Or you could have, and this is also a face-centered cubic. The other type is a body-centered cubic. So the attraction in your ionic crystals, remember, the ionic crystals, the ions want to pack themselves so they maximize the attractions, and minimize repulsions. Molecular solids will do the same. The more easily it packs together, or the better that you can pack your molecules together, the harder it is to melt. And remember, this is our closed packing. This is our hexagonal. And this was our cubic closed packing. So let's talk about molecular solids. They consist of atoms or molecules that are held together by weak forces. So your intermolecular forces. And this is what we talked a lot about in chapter 11. So you have your dispersion, your dipole-dipole, and your hydrogen bonding. They tend to be soft and have low melting points. Okay, so let's look at this chart right here. Okay, so here we have benzene that just has London dispersion forces. And here we have phenol, which has hydrogen bonding. And what do you notice about the boiling point? Benzene, which has the lowest molar mass, has the lowest boiling point. And then as our mass increases, our London dispersion forces get stronger, so it has a higher boiling point. And then finally, our hydrogen bonding has the highest boiling point. But what do you notice about the melting point? In this case, you see here, your boiling point for benzene is lower than the boiling point of toluene. But your melting point for benzene is higher than toluene. And why is that the case? Well, yes, this is more massive, but it kind of has this tail hanging off. So when you want to make a solid, so the opposite of melting it is freezing it, right? So if you're melting it, that means the solid has to be packed close together. And what is going to be able to pack close together? Benzene, which is nice and flat, or this toluene that has this tail hanging off? Well, as it turns out, benzene is more stackable. Okay, so the easier it is to stack, the closer your molecules can get in the solid phase, and the higher the melting point. Now, for boiling, they are not held together rigidly. They're flowing past each other. So toluene, since it's more massive and has its tail hanging off here, will have stronger London dispersion forces. And as they're sliding past each other, these London dispersion forces will have a greater effect, and that's why its boiling point is higher than benzene. So this is kind of weird, because you would normally think that the trend would follow exactly the same. But because benzene can stack better, they could get closer together when they're in the solid phase. And the closer they are together, the stronger their attractions, the harder it is to melt. This diagram over here is graphite. Graphite is an example of a molecular solid in which the atoms are held together with van der Waals forces. And graphite is used as a lubricant because you have these layers that can slide past each other. The strongest type of bond is the covalent network solid. Okay, atoms are covalently bonded over large network distances with a regular pattern. So basically, you have covalent substances that form crystals, and this is a very strong bond. So they tend to be hard and have high melting and boiling points. An example of this is diamond. Diamond's chemical composition is just carbon, but it forms a crystal structure. So let's review the types of bonding in crystal solids. First, we have our molecular, okay? And the particles that make up our molecular compounds are either atoms or molecules. What forces hold our molecules together? Your intermolecular forces. So you have your London dispersion, your dipole-dipole, and your hydrogen bonding. The properties of these, they are fairly soft. They have low melting points. They're poor conductors. Next, you have your covalent network. Here you have atoms connected in a network of covalent bonds. They form crystals. And the forces between the particles are covalent bonds, which are very strong. This is why this substance is very hard, very high melting point, because if you want to melt it, you're not breaking an intermolecular force. You're breaking a covalent bond, which takes a lot more energy than breaking an intermolecular force. They are poor thermal and electric conductors. And some examples are diamond, quartz, okay? They form crystals and they are made of covalent bonded substances. The next one is ionic, where you have positive and negative ions. And the attraction between these ions officially is called electrostatic attraction. This is very strong attraction. So this makes hard, brittle, high melting point, poor thermal and electrical conductivity. This also makes crystals. Some examples are table salt. And the fourth type of bonding is metallic. Again, the particles are atoms. Most of the time they are metals. And what's holding them together? Metallic bonds. Because the metallic bond has the core surrounded by these sea of electrons that can move, so if that's our crude drawing of it, you get a soft, or it could be very hard, depending on how many electrons you have. You could have low to very high melting points. They kind of do the whole range here. Excellent thermal and electrical conductivity. They are malleable and ductile. All metal elements form this. Okay, so they just gave us a couple here: copper, iron, aluminum, and platinum. Well, that is the end of part 2.